Welcome back. All right, let's continue to talk about types of volcanoes. We discussed cinder cone volcanoes, composite volcanoes. Let's talk about shield volcanoes. Now, of the previous two and this one, these are the largest of the three more common types: cinder cone, composite, or shield. They're very large, they're very broad, meaning very wide, and they look like shields from above. If you imagine looking at this shield volcano from above, it looked like Captain America's shield, kind of circular, kind of gently sloping down. So hence their name. The lava that pours out is very thin, so very low viscosity, very runny, basaltic in nature. So the lava, once it pours out, can travel for great distances down the very shallow slopes of the volcano. These types of volcanoes, over a number of eruptions, build up slowly over time. It could be hundreds of eruptions, creating many, many layers building on top of one another. This is how the Hawaiian Islands were created. These are not explosive by any means. They emit lava, little by way of gas or ash, or definitely no pyroclastic flows. So they have very gentle eruptions. They're very large volcanoes, but they just emit very low viscosity, runny lava, so they're not very dangerous to human life. The Hawaiian Islands, Mauna Loa, Mauna Kea, these volcanoes are all shield volcanoes. Again, basalt is the common rock here. So Mauna Loa, again, it's much wider than it is taller. You can see how wide it is, more very gentle slopes. It's not like the super steep composite volcanoes. Again, Mauna Kea, a very gentle sloping shield volcanoes. Now, I actually had a student last semester make a video for an honors project going over the common volcano types. Please watch this. It's a great summation, and a great video, great information about volcanoes. So please watch it. So that covers the three more common types of volcanoes. And then we have something called super volcanoes. They're extremely rare in Earth's history. Currently, there are 7 active supervolcanoes on land, so there are 7 supervolcanoes that could erupt. 3 of those, count them, 1, 2, 3 of them are in the United States. Yay! They are just unimaginably large in their eruptive ability. So by definition, a supervolcano must erupt a volume of more than 240 cubic miles of material. So a volume of 240 miles of material or more indicates a supervolcano. Just to give you some reference, when Mount St. Helens erupted, which is a major eruption, ash covered a few states in the United States. People were killed, the destruction that occurred. Well, the amount of material that was erupted from Mount St. Helens was only 0.29 cubic miles. So therefore, a supervolcano is over 800 times larger than Mount St. Helens eruption, just to give you a little reference. It's a very large magma chamber below ground. It just erupts entirely in one catastrophic explosion. After it erupts, so much material leaves the earth that everything else just kind of falls back down and creates a huge hole called a caldera, which the surface collapses into. Rhyolite is the common rhyolitic magma, common. Very high viscosity, very sticky, moves very slowly, a lot of trapped gas. So when it does erupt, there's a lot of pressure built up behind it. So here's a cool little formation of how these work. And you get a very large magma chamber. Again, this is rhyolitic magma, so it's kind of more in the crust area than melted material from the crust area, more so than in the mantle area. So this magma chamber developing in the crust, over 1,000 cubic kilometers, 240 cubic miles. You start to get so much pressure, it starts to force cracks, gas, ash escape through the fissures, ultimately in one large explosion. And then you get once the magma chamber is empty, then you get the collapse of the material over the magma chamber, falling in creating something called a volcanic depression called a caldera. Here's a map of the world's kind of more major plate boundaries in yellow, the ones with triangles, convergent boundaries, and then the triangles, you get super volcanoes. So you can see we do have some near boundaries, but some not near boundaries. All right, especially in the U.S. Long Valley is more so associated with the boundary. Yellowstone and Valley Grande away from a boundary. So these are just major hot spots underneath the North American plate. But you also get the Siberian traps near Japan, down in Indonesia, near New Zealand as well. So Yellowstone is actually one of the more famous super volcanoes. They make movies about it. There's always a new documentary about it. You may have heard of it, you may have not. Because the reason it's so famous, it's the largest supervolcano in North America, and it sits right underneath Yellowstone National Park in Wyoming. So Yellowstone sits above a hotspot that has erupted catastrophically 3 times. 2.1 million years ago, 1.3 million years ago, 640,000 years ago. You see a pattern there? About every 600,000 to 700,000 years, this erupts. So we're due. So it's been between 600,000 and 700,000 years since it last erupted. So we're due. So you have a large chamber, of magma underneath Yellowstone, just waiting to pop. That large heat reservoir, the large magma chamber, that's what creates all the geysers. So water superheated below ground, heats up, shoots out of the geysers. So Yellowstone's very famous for all the geysers and hot springs around. It's because it's fed by volcanic activity. Measurement. So this is a kind of a weird a little map. This measures the vertical change in ground level at Yellowstone National Park in a 4-year period from 96 to 2000. So what you see is, so you get this kind of circular change right here. So you can pretty much picture where this super volcano is. So you can kind of picture right where it is, right there. Again, another look at the rhyolitic magma below Yellowstone. The geysers created, earthquakes. This is a large, very, very large magma chamber. This indicates the number of earthquakes, as well as the cumulative. So this is the cumulative number of earthquakes. The red, the brown indicates just general number of earthquakes. You can see from 1975, a little swarm, a bunch, some, but you can see in the past. From 95 to about 2002, so it's a little bit older, you can see this area definitely has more earthquake activity than they had in the previous 20 years. Does that mean it's going to erupt? Who knows? If it were to erupt, so here's Wyoming, Yellowstone is in the northwest corner of Wyoming. If it were to erupt, this diagram shows the potential range of total destruction. Just anything pretty much in this circle, gone. Gone. Whether it's from the shock wave from the blast itself, ash, acid rain that's created because all this material getting thrown up into the atmosphere, pretty much in this area, yeah. Now, when this explodes, it's not a lot of lava. It's going to be mostly more ash, gas, those sorts of things. But in this area, just total destruction. Scary to think about. Before we go on, let me give you another part of the super secret code. It is the number 1. You got me? The number 1. I'll say it again. The number 1. So all this diversity in types of volcanoes and types of eruptions are tied to how and where the magma formed, near plate boundaries, what type of plate boundaries, maybe it's a hot spot. How and where the magma formed dictates the chemical makeup of the magma. Is it further down, making it more mafic and more runny with a lower viscosity? Did the magma come from melted material higher up in the crust, making it more felsic, more higher viscosity, so slower moving, sticky, explosive, The chemical makeup determines the viscosity of the magma. Again, less viscous is runny, more viscous is nice and thick. So all of that kind of comes back to here. Because basaltic magma comes from further down, kind of heavier elements, the chemical properties make it less viscous. So when it does make its way to the surface, very gentle lava eruptions, nothing explosive, form shield volcanoes. Intermediate, like andesitic magma, kind of intermediate viscosity, so somewhat sticky, mixing with water and carbon dioxide from this subduction event creates additional gas, so you get volatile gas mixed with sticky lava, or sticky magma, excuse me, forming explosive eruptions and composite volcanoes. And from higher up material, very viscous rhyolitic magma, very sticky, can get some gas content as well, super volcanoes. A lot of that's tied to silica content. The more silica, more quartz material, the more sticky it is, the more explosive it is. The more sticky it is, the more gas it will kind of trap. So, worldwide, here's a good, just a good summary map of volcanoes. Those are the red triangles. As you can see, most of them at or near plate boundaries. You also get these yellow circles, which indicate hot spots. Excuse me, hot spots are locations underneath the earth. Sometimes they create volcanoes like what we have in Hawaii, and these are typically away from plate boundaries. Sometimes they don't. But we can get, but we can get magma chambers below the middle of plates. But again, most times, most volcanic activity near the plate boundaries. Well, what about in Arizona? What about in Arizona? You know, we have volcanoes here. I talked a little bit about some of them in Flagstaff, but Flagstaff isn't the only place historically that has had volcanoes. Volcanic activity can be traced to Arizona almost 200 million years ago. So 200 million years ago, a lot of the volcanic activity, which would be what we now know as southern Arizona, so that's 160 to 200 million years ago. So a little break, and then 50 to 82 million years ago, you can see still southern Arizona, but a little bit more north. The yellow indicates volcanic activity 11 million to 38 million years, kind of central and western Arizona. The orange, as we get a little bit further north, you can see, you know, the volcanic activity keeps moving north. Well, why is that? A lot of times plate tectonics. So 5 to 16 million years ago, you see kind of central northern Arizona, and then 0 to 4 million years ago, Flagstaff, a big area, Springerville area. So even though it is a little spread out, but you can see how kind of over time, due to plate tectonics and for reasons of boundaries changing, hotspots, etc., you get the volcanic areas of Arizona changing. And a good portion of Arizona, almost, I would say, 70% of Arizona is near some sort of volcanic activity. The really only place that has little to no volcanic activity is kind of the northeast corner of Arizona, the Colorado Plateau. There's a lot of volcanic activity historically in Arizona. So that brings us to the end of igneous rocks and volcanoes. So this kind of side of the rock cycle. So what does that mean as far as what are the big or main ideas? Just remember the difference between magma and lava. Magma, where does it originate? What are the characteristics, composition, viscosity, temperature, etc.? And then as the magma or lava cools, the different types of igneous rock textures are created: phaneritic, aphanitic, vesicular, glassy, etc. Please review some of the extrusive hazards: lava, poisonous gas, pyroclastic flows, which is the most hazardous to humans, which is second most hazardous, and the different types of volcanoes: cinder cone, composite, shield, supervolcano, some examples of those, which is more dangerous, which is less dangerous, etc. So with that, it's been fun. That will close out Unit 6. Until next time, I'll see ya.